Hello everyone! I'm going to be telling you about the Big Bang and the future of the universe, which makes the end of this playlist on space physics. So if you go on the previous videos, you know that scientists came up with the theory of the Big Bang as the theory for the beginning of the universe, space and time. So this came around because Edwin Hubble, was looking at the distances of, or calculating distances of several galaxies, and he noticed that everywhere he would look, he would see redshifts, which means that things were moving away from us. So because everywhere, with the exception of Andromeda that I told you about, everywhere you would look, you would have redshift, it looks like space is expanding, everything is moving away from everything. So the theory began by thinking, okay, if space is expanding, then maybe if we run the expansion backwards, space was once in a very tiny little point, everything, all matter, energy, everything was confined in a place, and for some reason there was this rapid expansion outwards. Sometimes you cannot say there is an explosion. Sometimes in textbooks they do not accept explosion and they say it's a rapid expansion outwards. Other times you can say it's just an expansion, okay? So there was the Big Bang. There was a period that you don't have to know, but there was some inflation, and the expansion was even faster than the speed of light. But what happens is, at the moment, we know that the expansion is accelerating. So they say there was some deceleration at first, after this inflation period, and now the expansion is accelerating. Now, what can come after? Well, could we have that gravity that holds all the galaxies together actually stops the expansion, so slows down the expansion and gets things all to collapse back to themselves into a big crunch? And the reason why they think so is, if you imagine throwing an object up in the air, you can have the object moving away from you, but eventually gravity is going to make it go back to you. So that's the reason behind the big crunch. Is it going to be that we keep having expansion, but the expansion is not going to go, much faster, and I have this constant amount of dark energy, and therefore simply the universe is just going to die out cold because everything is far away from each other, so not even a new supernova could bring out the elements to do new stars, so everything is just very far away. So sometimes called the big yawn. Or could it be that the expansion keeps accelerating exponentially, which is what we are seeing at the moment, and everything is disintegrated, and we call that the big rip. So how is the universe going to end? Well, so first let me tell you about what we have, okay? I actually told you more about it before even telling you more about the Big Bang. So the Big Bang theory came from the fact that galaxies were moving apart from each other, as I told you. So it led to two important ideas. The universe may be expanding and has been much smaller in the past. The universe may have started by exploding outwards from a single point, which we call the Big Bang. Now, the thing that happens is, whenever you have a theory, sometimes people may not agree with your theory. Maybe they see things in a different way. So other scientists did not quite believe the Big Bang, and they believe in what we call the steady state theory. That said that the universe had no beginning or no end, so we wouldn't have to worry about the future of the universe. It was always there, just the way it is. It's just that the redshift was being observed because galaxies were being pushed apart from each other. And they were being pushed apart from each other because matter would enter the universe through white holes, which is kind of the opposite of a black hole, okay? So what you do? Well, if you have two conflicting theories, you need to search for new evidence. You need to find evidence that is going to prove your theory or disprove the other theory, okay? So the scientists thought, well, if the universe began with a Big Bang, then there should have been a highly energetic electromagnetic radiation being produced at the beginning, kind of an afterglow. And this highly energetic electromagnetic radiation would have been stretched as the universe expanded and became lower energy radiation. This is because as you stretch higher energy radiation, because they have higher energy, they have a high frequency and therefore a small wavelength. If you stretch space, the wavelength increases, therefore you have a lower frequency and a lower energy, okay? So that's what they said. And then in 1965, which actually earned them the Nobel Prize, the cosmic microwave background radiation was discovered. And this was great because actually their calculation said that this radiation would be at the time in the microwave region. So what is this thing, cosmic microwave background radiation? Sometimes you see it as CMBR, okay? So it's electromagnetic radiation produced in the early universe and has been traveling to space ever since. Because space is expanding, the wavelengths of this radiation have been stretched from gamma up to the microwave region. Now, a small point on this one. Some textbooks will say that it's gamma. I'm using using as a guidance the textbook from AQA that says it's gamma. Some other textbooks it says it's not gamma, it was light. I'm just putting what AQA is doing because I teach AQA and I don't want my students to go and you know, say something different. But just to give you a note, it's not completely clear if it's this gamma or not, okay? Anyway, the temperature that we would have in space would be of 3 Kelvin, much more specifically 73 Kelvin, which means it is about minus 270 degrees Celsius. And this again goes, so this temperature that we can measure actually corresponds to a microwave region by using Wien's law. Wien's law? Yeah, I think it's Wien's law. Now, this cosmic microwave background radiation has been and was mapped out using microwave detectors on Earth and space. It's very homogeneous, so it looks the same everywhere you look, and this is independent of the direction where you look. So there you go. There is a little bit there of what homogeneous means. Cosmic microwave background radiation can only be explained by the Big Bang theory. This is why at the present time, we believe that the Big Bang is the best theory to describe the beginning of space, time, and the universe, but and not now the steady state theory. But again, these are theories. If something new comes up, then we need to revisit the theories or change them, or even just say, no, it could not have been the Big Bang, okay? So be aware that this is something that, as many things in science, they keep changing. They can change if new evidence comes to light, and this proves that, okay? So at the moment, Big Bang is the only theory that we are accepting as the creation of the universe because it follows, or it can hold the evidence of the redshift that the steady state theory also had, but also the cosmic microwave background radiation, which steady state theory could not explain. Just as a tiny extra, and I'm not spending much on this slide, you are not requested to know, but just so you know, actually redshift and cosmic microwave background radiation are not the only two evidences for the Big Bang. The amount of helium in the universe is also an evidence, okay? This is because in the early universe you would be in a very hot space, okay? So hydrogen fusion could happen and it could form helium. And this explains the relative abundance of different elements in the universe. I'm not giving a lot of detail, but it's just so you know that there are actually more than just two evidences for the Big Bang theory, okay? So, we know how we started, more or less, or we have a pretty good idea of how we started. How is it going to end? I'm going to include these two videos in the description, but basically the fate of the universe, as I told you in the first slide, can be one out of three. Or at least at the moment it could be one out of those three. And this has to do with if the force of gravity is going to overcome the expansion. If it overcomes the expansion, I may get a big crunch. If not, I may keep, you know, expanding. Is either if I'm going to have a big yawn or rip. So, if the density of the universe, and that's where it goes down to, if the density of the universe is less than a certain amount, then it means that, because density is mass over volume, it means that I don't have a lot of mass for the space that I have in the universe. So I kind of cannot have enough force of gravity to overcome the expansion. So my universe expands forever, where I could either end on a big yawn or a big rip, depending if the acceleration stops happening or not, or depending if the expansion keeps having this acceleration or actually stops accelerating. If the density of the universe is higher than a certain amount, then it means that I have more mass per amount of space. So because, you know, masses attract each other due to the force of gravity, it means that gravity could take over, the universe would stop expanding, it would actually reverse the expansion, and I would end up with a big crunch. And all of this has to do with how much dark matter we have, how much dark energy we have. So dark matter is matter that exists. We know that exists because otherwise we couldn't explain certain things in our galaxy alone, like the velocity that stars are moving around in the galaxy. So we know that we exist, but it's dark or is invisible to us, so we call it dark matter, okay? And is an attractive force. Einstein came up with that first, and unless I'm super wrong, but no, it was Einstein. So it kind of is an attractive force. It's like, you know, it gives or it helps out the gravity, right? While the dark energy is kind of an anti-gravity because it produces a repulsive force. However, dark energy, again, because it is invisible to us, and we just call it, you know, energy. So we have dark matter versus dark energy. I don't know much about the two of them. Like, we scientists don't know much about the two of them. We just know that we cannot see them interacting with light. We don't see them, they don't reflect, they don't shine. We don't quite know what is going on, but the calculations suggest that both exist, okay? Together, the calculations say that they make up to 96% of the universe. And again, we cannot see either of them. And I told you already, but the astronomers know that dark matter exists because the visible matter does not have enough gravitational pull or symbol to hold the galaxies together. Okay? Now, if I go on the most recent studies, there are some studies that are saying, oh, dark matter and dark energy don't exist. Now, again, I cannot say much about it because, you know, in science you need to leave some space and time for people to actually figure out which is the best theory. Just like years ago we had the Big Bang in the in the steady state. So I'm not going to say much about it, and at the moment, if you are being tested about this subject, you may know that maybe they don't exist, but it seems like they are in here, that they are here in the universe, okay? So that is it for me, I believe. Oh, this is just a visual representation. So imagine that the dark energy is like balloons. They are trying to pick up a weight, and the dark matter is trying to make that weight go down and to, you know, not to have this universe being compressed, okay? But that's just, you know, a visualization. These two videos, I'm also going to put on the link, which in the first one you have a discussion about what is the fate of the universe, and the second one is a recent one about what it seems like is happening at the moment with the universe, and if that is really what is going to happen, how is the universe going to end, okay? So, I hope it made sense. If it didn't, please let me know. Message me, talk to me in person, all that stuff. And up to then, be happy and healthy. Bye!